Hi, everyone, and welcome to our next topic. So, today we begin looking at some more advanced differentiation techniques. So, up to this point, we've talked about all the basic derivative rules. So, that's our constant rule, our power rule, constant multiple, sum and difference. And then we looked at some of the more basic function types as well. So, sine and cosine for our trig, and then our exponential e to the x or a to the x, and then natural log and log base a, so non-e bases. So those are all the initial function types that we need to worry about, but not every function is going to fall into just one of those boxes. So today we're going to start to look at some more advanced functions and how we calculate their rates of change as well. So the first thing we're going to talk about is contributions to a derivative. So when a function is the sum or difference of two terms or more, its derivative is the sum or difference of each of those terms. We've already saw that with the sum and difference property or derivative rules. So that's because each term in the original function contributes a value to the y value of the function, and then those different values are added or subtracted. So that means each term also contributes some kind of change to the derivative, which is then added or subtracted. So that's not exactly how it works, though, when a function is made up of two or more factors being multiplied or divided. But in that situation, each factor still makes a contribution to the derivative, but their contributions are being multiplied by another factor. So we have to account for how each factor changes relative to the other. So what that produces is a product rule. So when we start with a function that is the product of two factors, so we may see functions that are products of more than two factors, in which case we have to do like a product rule inside of a product rule. It becomes a whole thing, but it is possible. So, but we're going to really focus on products of two factors to begin with. So when we do that, we have a function f and g as the product, and that's our original function. So to find the derivative of that product, the rule is we take the derivative of the first multiplied by the second original, and then we add it to the original first function multiplied by the derivative of the second. Or how I like to write this to help us kind of organize this information is we're going to make a list of four pieces. So I'm going to start with my first function, a, its derivative a prime, then my second function b, and then its derivative b prime. Or if you rather use the f notation, we can think of this as f of x, f prime of x, g of x, and then g prime of x. So we list out the four pieces, and then we're going to make their product. So we start with the interior first. So I'm going to take the inside two and multiply them, and then add that result to the product of the outside functions. So that end result turns into f prime times g of x plus f of x times g prime. So this little organizational trick is really, really helpful when we are dealing with any kind of product rule, no matter what the function types are. So just keep that in mind as you guys are watching these examples. You're going to see me um, type up or write out the four pieces for each one of these problems. So just keep that in mind as you see these. You're going to see how helpful it is. All right, so if we take a look at this first example, now for the first guy, this is a polynomial times a polynomial. Traditionally, when we use the product rule, it is only really helpful or necessary when we are taking the product of any two functions where both of them are not polynomials. Now we can still do the product rule for this problem, but it's not necessary to use the product rule here because we have the ability and the knowledge to just simply multiply this guy out. So I'm going to do that first. I'm going to rewrite this function and just multiply it together. So when I do that, I'm going to actually set up a little box here. If you're not a fan of the box method, I feel sorry for you because the box method is so fast and easy and organizes everything. So 15x, 12x squared, negative 10x squared, negative 8x cubed. I'm going to go ahead and put this in standard form for the result. So I get negative 8x cubed plus 2x squared plus 15x. So this is the other form of this expanded polynomial. So because when you start with a polynomial times a polynomial for your f and g functions, you always have the ability to multiply them out and just get a long string of polynomial terms. So this is really just a power rule problem. So we would get negative 24x squared plus 4x plus 15. So this is the answer. But the reason why I'm starting off with an easy problem where it's unnecessary is to show you guys how the product rule works and the fact that it will get us to what the right answer is supposed to be. So I know that this is what the final answer is supposed to be. So if I try to attempt this problem using the product rule, again, I'm going to identify my A and B or F and G, however you guys want to refer to it. The reason why I like A and B sometimes is the name of our function is f of x. So some people like to name the two pieces F and G. That just gets confusing when the function's name is already one of those guys. So that's why when I write it out, you guys are going to see me do A and B. So again, I need my four pieces, A prime, B prime, always in that order as well, okay? Now, technically for a product, it doesn't matter which one is A and which one's B, but it really doesn't make any sense to reverse that order just to be stubborn or prove a point. So just keep it consistent. That way you guys are always following the same routine. It's definitely helpful. So my A function is 3x minus 2x squared, whose derivative would be 3 minus 4x. So just using power rule there. And then my B function would be 5 plus 4x, whose derivative would just simply be 4. Remember, derivative of a constant is 0, so it disappears. So now I'm going to take my inside pieces and multiply them, and then add the product of the outside pieces as well. So what I get as a result there, I'm going to write it out long form first. So this would be 3 minus 4x times 5 plus 4x. So that's my F prime times G, or A prime times B, plus then the product of the outside pieces. So even though the order might seem the 4 goes last, I like to keep my constants in front of binomials. It's easier to read and stay organized and not forget something hanging out in the back. So that's the long form of the answer. Again, that is A prime times B plus now I changed the order up, but it's still essentially A times B prime. Again, I flip-flop these two just to make it look nicer. So this is just following the product rule definition. So after that, it's just a matter of simplifying and cleaning it all up. And again, this is always going to be a part of the process. We want the derivative in the nicest form possible because a lot of times we're going to do stuff with the derivative afterwards. So we wouldn't want to leave it like this. It's better to multiply and expand everything out. So when I do that for here, again, I'm going to do a quick box rule. Again, if you can do this in your head, then by all means do it in your head. Just make sure you're getting it right. If you can't, box rule is here to help organize and get the right answer. So that's going to give me negative 16x squared minus 8x plus 15. And then distribute the 4. So that gives me 12x minus 8x squared. Combining your like terms leaves us with negative 24x squared plus 4x plus 15. And surprise, surprise, we do in fact get the exact same answer. So again, this now some of you may view that as, well, this was totally redundant. I don't need the product rule. I could have just multiplied it out and gotten my final answer. Yes, that is true if both of your factors in the original product are polynomials. Again, if you come across a problem like that in the future when you're doing this on your own, then product rule will never be necessary if it's a poly times a poly. But if it's any other function combination, polynomial and an exponential, polynomial and trig and exponential, trig and natural log, or any logarithm, any other combination of function types that you guys know of right now, it is absolutely necessary for us to use the product rule. You're going to see that here in this next example. So now I have f of x equals x times e to the x. So again, it's important when you're starting to identify your factors. So rewriting it with a multiplication symbol in between sometimes is helpful. So x times e to the x, so x is my a, e to the x is going to be my b. So just for these first few, I'm going to keep writing out the 4 names of these functions, a prime, b prime, but that's not necessary. You guys don't, once you establish the habits and you understand the routine and process, you can kind of do away with that. But my first function, x, has a derivative of 1. My second function, e to the x, remember derivative of e to the x is itself. That's that special, super easy one. So inside times the, or multiplied together plus the outsides. So my f prime of x function would result in e to the x plus x times e to the x. So pretty straightforward, simple derivative. But then after the fact, um, if you look at different textbooks on what's the best form to leave your derivative in, it to me it's always been about what's your plan with that derivative function. Are you going to use it to evaluate? Because if we want to plug numbers in, then we want it in certain kind of forms. We don't want like terms left over. We like to combine it so it's easier arithmetic. Are you going to try and solve the derivative by setting it equal to a value and then do some math afterwards? Because if that's the case, then leaving it in factored form is really helpful. But for right now, when we're just learning how to find the derivative, it's really just a matter of get all your like terms combined, make sure that there's no like terms left over in extra places that could have been condensed. After that, it's really more of a personal preference or doing what the directions say. Now, just so you guys are aware of things that we can do with them, I do want to show you different ways that we could rewrite this that may be helpful later on down the road. So one of those things that we can do to simplify derivatives, or not necessarily simplify, but rewrite them in different forms, is factoring. That is helpful when we eventually we will be trying to figure out where these derivative functions are equal to certain values, mainly zero. And when that's the case, then it's really helpful to put things in factored form. So looking at this guy, both of these terms share a common factor of e to the x. So an alternate form of this guy that you may see in different textbooks or stuff would be factoring out the e to the x, which would leave us with 1 plus x inside. So both of these are acceptable forms of this derivative. It's just a matter of what's your preference or what are the directions asking you to do. So which one would be better suited for different situations. But if all they asked you to do was find the derivative, most of the time I would probably just leave it like this guy. There's no extra factor or extra like terms in there that need to be combined or anything like that. Okay, let's try another one. We got some trig now. So now this has two terms. Again, each term has to have its own derivative evaluated on its own. So for this first term, 2x cosine of x, if I were to try and break that apart into factors of the product, technically looking at that, it looks like there are three pieces. So one thing that I want you to keep in mind is if you ever try to set up a product rule or quotient rule when we get there, and one of your pieces has a derivative of zero, then what you were doing was either unnecessary or you didn't set it up in the correct way. Because if one of your pieces has a derivative of zero, then that piece, the original function, was a constant. And constants don't count towards creating a product rule or a quotient rule problem. So you have to always keep that in mind because, yes, there is a factor of 2 in this product, but we could simply rewrite this as 2x times cosine. So by grouping factors together, we can keep it as an a and a b being multiplied. So that's one strategy that you guys want to always keep in mind. So kind of rule of thumb, anytime that you have a coefficient, a part of a term, that guy is automatically just going to join the party of whatever the first actual non-constant function is. Okay? So instead of x and cosine and then also multiplied by 2, we're just going to make it 2x times cosine. So 2x will be my a, cosine will be my b. So I'm going to try and do this without the four labels this time. So first function, 2x, has a derivative of 2. Second function, cosine, remember it starts with a c, so its derivative is negative, and we get negative sine of x. So we're going to take inside functions plus outside functions. So we're starting with y notation, so we're going to write dy dx instead of the f prime. Equals, inside product would be 2 cosine of x. Outside product, remember it's normally addition, but if either of these guys are negative, then that results in a negative product. So I don't want to write plus minus, or plus a negative. So I'm going to write minus 2x sine of x. Okay. Now, one word of caution. Technically, um, if these guys were flip-flopped, if I had made cosine my a and 2x my b, then uh, we could have ended up multiplying these guys in the reverse order. Now, one word of caution. Don't ever write a product of a trig function and really anything else in this order. Anytime that we write trig functions being multiplied by other types of functions, when you write that other type of function as a factor after the argument of the trig function, this can be very misleading and easily misinterpreted as this 2x being a part of the argument of the trig function, which is not the case. So, some strategies to help with that: get into the habit, if that's something you struggle with, get into the habit of putting parentheses around your argument for all of your trig functions. If you always do that consistently, then you should never have to worry about it, because if this guy wanted to be in the argument, it has to be inside the parentheses. But the best strategy is always moving these factors out in front. So anything that you're multiplying a trig function by should always go out in front of the trig function. Then you don't ever really have to worry about that. So myself personally, I use parentheses around the arguments of the trig functions anytime that the argument is not just x. If it's just x or just theta or t, then it's not something that I typically worry about. But anytime it's something different, then I'll put the parentheses around it. And I always make sure that my extra factors are sitting out in front. So just those little things can help go a long way, help make sure that you guys are keeping everything straight. All right, so these two pieces of our derivative both came from the derivative of this first term in the original equation. So now we have to take the derivative of the second guy. So this is not a product. Again, some people may look at that and mistakenly think that my two pieces are -2 and sine of x. But if you set up a product rule for that, -2's derivative is 0, and then we have sine of x and cosine of x. And again, you could do a product rule for this, but what you're going to see happen is, because this derivative is 0, the first product of these pieces is 0 times sine of x, which is just 0. So you'd literally just end up with -2 times the cosine of x, which is really what this derivative is supposed to be. So you can do the product rule or the quotient rule with those pieces, but you're doing extra work that's unnecessary, and it's probably going to lead to some kind of mistake at some point. So just recognize coefficients do not count as something making this a product rule or a quotient rule problem. So -2 sine of x, again, this is just a constant multiple, not a product. So this just yields -2 cosine of x for the other piece. So we have all of our pieces for the derivative. Now we just take care of any simplifying. And in this case, we actually end up with two terms that are opposites and cancel each other out. So we end up with dy dx equals -2x sine of x as the derivative function. All right, now we're going to take a look at the flip side of this. So when we start with a product of factors in our original function, we use the product rule. But when we start with a quotient or a fraction, then we have to use the quotient rule to find its derivative. So it's a similar process as far as identifying the pieces, but the formula for it is much more complicated. But if we follow the same setup, then it's a little bit easier to help us remember the rule. But essentially, we have to look at how each factor of the fraction changes relative to the other one, but then we have to keep in mind that it's also a fraction, so it ends up being or having a denominator. Now, both of these rules have proofs that work out through the limit definition as to where these formulas come from. So if anybody's interested in that, you guys can always look it up on YouTube or online. I'm sure there are videos for actually watching the proof through the limit definition. It's very complicated, but I'm sure some of you guys can handle the explanation behind it. So if you're interested in figuring out where the formulas come from and why we end up using these guys, that's where it comes from. Again, that's stuff that Isaac Newton and Leibniz did centuries ago to figure out all those things for us. So the rule here, if you notice, the order is actually the same. Now, some textbooks write it in different orders, but it really doesn't matter. Again, if this is my A up top and my B on bottom, then we take the product of A prime and B first, but instead of adding like we did for the product rule, we subtract. Again, that's a major difference because it's division. So it's minus, and then we take the original A and B prime. So it's still, when we make our list, it's still going to be the inside products and then the outside, but we're going to subtract in between. And then the big piece to remember is the original denominator gets squared to create this derivative. Now, one thing that we have to keep in mind is that the original function derivative cannot equal 0. So what that means is any values of x that would have made the original function equal 0 in the denominator automatically get removed from the domain of the derivative, which shouldn't make or shouldn't be too concerning because that's something we've talked about as far as differentiability goes. If there are no points on the original graph, then there's no slope there either. So those vertical asymptotes of the original function show up as vertical asymptotes of the derivative as well. All right, so let's just dive in and try one. So um, technically speaking, when we did the product rule, the first example was a polynomial times a polynomial, and the product rule is unnecessary. Technically speaking, with polynomials divided by polynomials, there are strategies around this. I could use some long division to rewrite this guy as a string of polynomials plus one extra little fraction, but even that guy would still require some kind of rule, either the quotient rule or the next one we're going to learn, which is called chain rule. But that would be a lot of extra work that is really unnecessary and would make it more difficult. So when we have polynomials divided by polynomials, you will want to do the quotient rule for them. Okay. So I'm going to start this off again. I'll start with the labels here first, just for the first couple here to get you guys used to it. So A prime, B prime. So our numerator is a always, so just go in order. So 5x minus 2, its derivative would be 5. And then our denominator, x squared plus 1, its derivative would be 2x. So we're going to take insides minus the outsides now to set this up. So for f prime of x, inside product, I'm going to write it out long form first, and then I'll show you guys the result. So 5 times x squared plus 1 minus, and then the outside. Again, the order of this multiplication, write it how it makes the most sense to you. So even though I'm going to do a first, because it's a binomial, I'm going to move the single term b prime out in front. So 2x times 5x minus 2. The most commonly made mistake with the quotient rule is you guys forget that it was a fraction to start, so it automatically has to be a fraction in its derivative. That's always the case. So because of that, we have to remember that the original denominator gets squared, okay? So now we can expand and condense or combine like terms in the numerator. The one thing that we don't really ever have to do, some people choose to, and if you guys want to, you can, is expand the denominator. There's not really anything that we're going to do throughout the course where expanding the denominator will benefit us. It's really just extra work. Some people, when they teach this course, may require it. For me, it just seems like something unnecessary and a waste of your time. The only reason that it might be beneficial is if the entire denominator in expanded form ends up looking recognizable as a multiple of the result in the numerator, but that rarely occurs. It would be very, very unlikely for that to happen. And if it does happen, it would also be true that the top would factor and have a common factor with the denominator. So realistically, it's just not necessary. So my common practice will be leaving the denominators in squared form. Very rarely will I do anything to that bottom, but the top guy I am going to distribute, and then we can combine these like terms. So I get 5x squared plus 5, and then minus 10x squared plus 4x. So do remember about the negative that you're sending in when you do that. And so our final form in this case would give us negative 5x squared plus 4x plus 5 all over x squared plus 1, quantity squared. So that's how I'm going to leave it. Now, again, there may be rare occurrences with these polynomial over polynomial rational functions where this numerator could factor, and there may possibly be a common factor linked between the top and the bottom, which would help us reduce. That very rarely occurs, though. And it's not a common thing with these problems. You can explore it and try, but I mean, with a quick glance, this would be a quadratic trinomial, so we'd be looking for the AC method to apply. So we would need factors of negative 25 that add to give me 4. 25's only factors are 1 and 25 and 5 and 5. Neither of those combinations with positive and negatives would yield a positive 4. So there's no way that this guy is factorable. So there's not really anything that we can do to that. And even if there were, there's not much benefit to doing that. So we are going to leave it as is, and that is our final answer for that derivative. All right, so for the next one, I want to find the equation of the tangent line to the graph of f of x equals 3 minus 1 over x all over x plus 5. So for this guy, this one is a fraction to start, but if you notice, is what we call a complex fraction. It's a fraction that has a term within either the numerator or denominator that itself is also a fraction. So we don't like to use the quotient rule for this because it requires extra rules inside of it. So whenever you guys have something like this, you want to, there are a lot of problems where we have to do something to the original function that makes the calculus easier. That's one of my biggest recommendations. Always do complicated algebra first to rewrite or manipulate the function so that it makes the hard stuff, the calculus, as easy as possible. Because it's really difficult to do it in the reverse order. If we can avoid the algebra stuff and make that part easier, but all that does is make the hard stuff even harder. So we're going to fix this guy. The simplest way to fix a complex fraction: identify the denominator of the difficult part, the thing inside of the fraction. Then we just multiply all of the numerator and all of the denominator by that little fraction's denominator. In doing so, we are going to get rid of what's making this a complex fraction, which is this term. So distributing x to both of these guys just yields 3x minus 1 in the numerator. And then on bottom, we have x squared plus 5x. So we got rid of the complicated thing. Now this just looks like another problem similar to the first example. So my top 3x minus 1 has a derivative of 3. Bottom x squared plus 5x has a derivative of 2x plus 5. So we'll do insides minus outsides. So we get, and again, I'm going to do long form. I highly recommend these first few that you guys write it out long form. Yes, it's more writing, but it's definitely more helpful to see all the pieces until you get used to this process. And then our original denominator squared. Okay. Oh, I got the squared. All right, now, when your second two pieces, so my A and my B prime are both groups, so binomials, trinomials are bigger, it is very easy to forget that we need to distribute a negative to whatever this product yields. So sometimes when I'm doing problems in class or on my own, sometimes I'll actually write the results of this expansion above just to save a little bit of space and time. So that's what I'm going to do here. So I'm going to have 3x squared plus 15x is the result of distributing here. But this spot, I'm actually going to write the trinomial result inside, and then I can distribute my negative. That way I know for sure that I didn't forget to do that. So this would yield 6x squared, 15x minus 2x, so plus 13x, and then minus 5. So that's the result of just the product here. Now I have to subtract all of those pieces, so I'm going to change the sign. So this becomes plus, negative, negative, and positive. Now I can go ahead and combine my like terms. So we end up with negative 3x squared plus 2x and plus 5 all over x squared plus 5x quantity squared. Now, again, you can try and explore, see if the top is factorable, but even if it is, it's not a guarantee that it's going to actually yield a better form or an easier form of the derivative. It may, but most likely it's not going to. Now, in this case, one thing to keep in mind, this bottom guy, even if the top factors, it's not going to yield a factor that is identical to this guy because this guy actually has a factor of x and x plus 5 inside that's being squared. So realistically, that bottom could be rewritten like this. I could pull out the x from the inside of here and square it and square x plus 5. So if the top has any common factors, it's got to be one of these guys that would allow us to reduce it. And odds are it's not going to be that. I can make negative 15 with A and C, and then I need to make 2. And it is possible to do that with 5 and negative 3. So this guy is going to be factorable. It's just not going to help us with the denominator because I would need 5x, negative 3x, and then plus 5. So this guy is going to factor. I'm going to pull out a negative x from this to leave me with 3x plus 5. This guy has a negative 1. So this numerator actually factors. I'm going to pull out a negative 1 from both of these to leave me with x plus 1 and then 3x plus 5. So even though it's factorable, it doesn't mean that it's going to make your lives easier to do that. Like that was a good bit of extra work that we had to do there. Now, again, if the problem said, now figure out something extra, figure out the value of the function when x equals or the derivative when x equals 0 or something along those lines, then this may be beneficial. But for what we're doing right now, it's actually not going to be all that helpful. So this is a further step in rewriting the derivative, but it's not going to be something that is actually helpful to us. So I'm going to get rid of it for right now, just so it's not going to mess anybody up with this next part. So one piece that is actually missing from here, I'm not sure why it didn't get printed, but we want to find the equation of the line tangent to this function, and we need a point. So we're going to use when x equals 1 as our point. So remember, for equations of tangent lines, the form is y minus the y-coordinate at the point of tangency times the derivative's value, or the slope of the tangent line at the point of tangency, times x minus the x-coordinate at the point of tangency. So the x-coordinate, or c value, is 1. So I'm going to find the y-coordinate. So let's plug 1 in here to the original function. So we can do the original form, or this guy is actually going to be easier to work with. So after we got rid of the complex part. So if I plug 1 into here, it gives me 3 minus 1, or 2, over 1 plus 5, so 6. So the y-coordinate is 1/3. Okay, so that's my f of c. And now I need to know the slope of the tangent line at x equals 1. So for that, we will use the derivative. So another reason why it would be unnecessary in this situation to go through that factoring process is no matter how it factors, we still just need to plug a number in here. So it's just as simple to plug it into the form that we have. So in this case, that would give me -3 plus 2 plus 5 in the numerator. And on bottom, we know this bottom guy is 6, and then we got to square that. So -3 plus 2, plus 2 plus 5 would give me 4 over 36, or a slope of 1/9. So I've got my point of tangency, I've got my slope. So the equation of my tangent line would be y minus 1/3 equals 1/9 times x minus 1. And that is my equation to that tangent line. All right, so for these last couple of examples, I just want to demonstrate some ways that functions can look at the beginning that may lead you down the path of trying the quotient rule, but it's actually unnecessary. So there's just a couple different variations where that can happen. But again, one of the tricks that you guys can remember when ever you try product or quotient rule, if one of those derivative parts, so your a prime or b prime in the setup, ever end up being 0, stop what you're doing because you're not doing it the best way, or possibly not the correct way to find that derivative. So for example, this first one, y equals x squared plus 3x over 6. So one way to help you think about it is the categories of functions. So even though technically a constant function could be considered a polynomial, it really is in that family of them. As far as derivative rules go, it really is its own separate thing because our polynomials require the power rule. A constant function does not require the power rule. The derivative of every constant is 0. So with that in mind, constant functions are going to be their own separate category when it comes to identifying functions for derivative rules. So if one of your functions is ever a constant, then we definitely don't want to do that quotient rule. But so keeping this in mind, if I tried to set up the quotient rule for this guy, our top piece, x squared plus 3x, that's a polynomial, so nothing crazy there. But then that bottom guy is a constant function, so its derivative would be 0. So again, when I go through the process, that second group of factors that I would be subtracting, it's just going to cancel each other out, and you're going to be left with 0, and then we're going to have extra stuff. So this one actually gets really complicated if you try doing it that way, because I would end up with 6 times 2x plus 3 minus 0 times that group, or just 0, divided by 6 squared. So it looks way more complicated than it needs to be. And what ends up happening is you produce extra factors on top and bottom that you then have to simplify or cancel out to simplify the overall result. So again, if you get that 0 as one of your two derivatives, stop what you're doing. It's not the best way to do this. This one, instead, we do some algebra beforehand to make the calculus easier. So the algebra that we're going to do ahead of time is a simple strategy of reducing or separating and reducing fractions. So whenever you have a fraction where the denominator is one term, we can break this apart and simply turn it into two separate fractions and try to reduce them. A lot of times the fractions will just disappear, or we can rewrite it in a simpler format. So this is the reversal of combining fractions. So if I had given you 1/2 plus 3/2 as a elementary school problem, well, we have common denominator, so we're allowed to add the numerator. So the step that we don't typically write out, we just do it in our head, is rewriting it where those numerators are being added, and we see that, and then we can simplify it, or the result. So all this is the reversal of that. So if I had common denominators and I combine them, if I started with them combined, I can just simply separate them into individual fractions where each term of the numerator gets its own fraction with that same denominator when we separate it. So if we do a little bit of work here first and separate this, now we can see that this is just two power terms. And if we need to rewrite a little bit further for you to see that, this is really 1/6 times x squared plus 3/6, which reduces to 1/2 times x. So this isn't quotient rule. This is actually just two power rules. So for dy dx, we bring down the 2. We get 2/6, which reduces to 1/3 x. And derivative of the linear term is just that coefficient, 1/2. Now, after that, if you wanted to combine this back together to write it in that same fraction form, you can. It's not necessary, but you can if you really wanted to. So just keep that in mind. This strategy of splitting and reducing fractions shows up all the time in all kinds of various ways. So be on the lookout for that. Second one, again, it looks like a quotient. It technically is a quotient, but it's not a quotient of two polynomial functions or functions that require power rules or other function types. So in this case, this would be a case where we just simply rewrite it as that constant multiple out in front multiplied by that power term. So our derivative would just be bringing down the 4, 28 reduces to 5/2 times x cubed. So it doesn't require quotient rule there. Now this one looks way more complicated than the first two. But again, we just need to do some algebra to make this simpler. So the first algebra I need to do is just distribute that -3 inside. So again, -9x plus 6x squared all over 7x. And yet again, technically this one really is a product, or excuse me, a quotient. We have an x in the denominator. But this is a case where you could do product rule, but we can avoid it by splitting the fractions and reducing. And the only thing that lets us do that is the fact that the denominator is one single term. If this was a +1, then we wouldn't be able to do that, and we'd have to do the quotient rule like the first example. But in this case, we can separate this. Again, we just separate the terms out. Each one gets its own fraction. So we'd have -9x over 7x plus 6x squared over 7x. So now these become fractions that we just simply try to reduce with exponent properties. So for the first guy, the x's are going to cancel each other out, and we're actually just left with a constant here. So this becomes -9/7 plus, for the second guy, 6/7 is the constant multiple. I'm going to pull that out. And then x squared over x, that just reduces to x to the first. So what was a complicated rational function to begin with, and it still is, the only exception to that, these guys are the same function. The only difference is this is a linear function. This is a rational function with a restriction where x is not allowed to equal 0. So technically, if we were doing a formal proof or something along those lines, we would want to identify that this linear function cannot use the x value of 0. So this is actually a linear function with a hole on it at x equals 0. But to find the derivative, that part's not really a part of the process. To find the derivative, the only rule we need here is constant rule and power rule. Derivative of a constant is 0, so that guy disappears. Derivative of this linear term using the power rule would leave us with just 6/7. Or another way of interpreting this result is this original function has a rate of change of 6/7 everywhere except at x equals 0, because again, that point doesn't exist, so it wouldn't be differentiable at x equals 0. So there are some cases where we actually do have a polynomial over a polynomial, but because it's a single term polynomial in that denominator, we can split it. So as long as we have polynomials everywhere and one term on the bottom, when we split this, no matter what the exponents are on those x variables in top or bottom, they will always simplify or reduce down to something that we can rewrite and use the power rule for it. So that's one nice thing about just working with polynomials. And then this last guy, yes, we have an x in the bottom. This would be a case if we tried to do the quotient rule for it. The first guy has a derivative of 0, and then the bottom guy. So if we did it this way, the inside product would be 0, and then we'd have our result. But again, you can do it that way, but it's really extra work that is unnecessary, because instead of doing all that, we can rewrite this so that the power rule fits the format of the function. I can bring the x squared up top and make it x to the negative second and pull out the coefficient 9/5 out in front as our constant multiple. Now we can just apply the power rule, so we would get negative 18/5 x to the negative third, or if I fix the negative exponent, negative 18 over 5x cubed. Now, if we had done the quotient rule, you would have ended up with some factors on top and bottom, and that we would actually have to move the negative exponent down and or reduce the powers of x. But either way, what we would end up with is this final answer. And that is it for the product and quotient rule. So now you guys are ready to try some of these problems on your own.